We'll start with our quick look at the calendar. So last class we talked about density. Today we talk about work, and next class we talk about economics. And I wanted to highlight those 3 days because project number 6, which is now on the table, so go ahead and grab one, contains exactly 3 questions. 1 density problem, 1 work problem, and 1 economics problem. Of course, these questions have like a dozen parts each, but there's only 3 questions, and they are about those 3 topics. And I'll also point out that density and work and this economics thing we're going to do on Wednesday, they all have like formulas that involve integrals, but you're not going to be using any of those formulas on this project that I've just handed out. You're going to be building things by slicing or cutting into slabs just like we did last class and like we'll continue to do today, okay? All right, also project number 5 is due right now, so go ahead and put the chocolate project in the folders. And once you've done that, you are free to eat that chocolate. And let's go ahead and jump in at the top of page 58 with our summary. Can we go to Alex? Okay, Sam, 0. Okay, number 1, Rob. Okay, so then if we, so today we're going to talk about work involved in moving things, and oftentimes the work that we calculate will be work done against gravity. And so on Friday, I talked about how I was misusing the word mass. Sometimes I was referencing weights, but still calling them the mass. So today we're going to be really clear about that distinction. If you have a mass, then you got to turn it into a weight by multiplying mass by the acceleration. And then once you know that weight, say, well, wait a second, weight here is just the force, which means that the weight is really mass times acceleration. And then if I want to multiply by distance to turn it into work, we get that, okay? So work is force times distance, but if it happens you are not given the force, you are not given the weight, then you need to go mass times acceleration times distance, okay? So we're going to use one of those 2 in each of the problems we do today. I think if you're in a vacuum, I don't believe there's any resistance. Is there work? But if there's no resistance, how is there force? Is it? Look at the equation, force on distance, it is moving. But once it's moving, there's no more work, right? If it's just floating freely in the vacuum. Yeah. No mass. Yeah, mass happens wherever. Yeah. So mass exists without. Mass exists all the time. Mass is a constant. Weight is something that changes depending on whether you're on Earth or on the moon or floating in space. Work has to do with the weight, yes. Okay. All right, so there are some units that are listed here. You've got what everybody else in the world uses here, and then you have what we use here. There was no judgment there. And so, so just be careful about, just be clear which column you're in and which row you're in. Okay, so let's try number 2. Okay, so the weight of 1 kilogram of iron. So if we're going to find weight, we need to multiply mass by acceleration. That kilogram is a mass, right? Kilogram is up here in the mass row. So the weight we know is mass times acceleration. You may have seen that in physics as F equals ma as opposed to W equals mg. So the mass in this case is 1 kilogram. Acceleration due to gravity is 9.8 here on Earth. So the weight of 1 kilogram of iron here on Earth is 9.8, and then what are the units for weight? Is newtons. You have to call it weight. As opposed to? Oh, you could just call it force. Yeah, weight and force are synonyms. Yeah. Okay, let's go to 3. Rich. How much work is done right there? Okay, so here's where we get to start using our work equation up at the top. So we'll say work equals So work is equal to force times distance. The force we've just found. It's this 9.8, okay? But if you didn't find that already, then you're using the mass times acceleration times distance formula. So I'm just going to use that, and we'll rebuild what we just did in 2. So mass is still 1, acceleration is still 9.8, and the distance in this case, 3 meters. So we are working to lift this thing off of the floor and raising it 3 meters up in the air, and we crunch this together. What is this? 29.4?
Yes.
So units for work. Yeah, it's a Newton meter or a joule.
Kilogram meter per second.
Times meters. No, no conversions. I mean, we can, if we have a problem that's in the English units, we'll stay in the English units. Yeah, we're not going to be converting between the two. Kilogram meter per second squared times meters. Yeah. Okay, so let's try 45. We'll actually do some calculus. How about that? All right, Sephora, 45. Number 4, I mean. Okay, so we've got this rope. It's 45 meters long, and all we're going to do is drag it. Maybe there's some pulley up here, so no friction that we're worried about at the top. We're just going to pull it up, up, up until it's completely cleared of this cliff. So let's answer this the wrong way, and then we'll do it the right way. So the wrong way, we'll just do our standard work equals mass times acceleration times distance, right? And the mass of the rope is 30 kilograms, so this is 30 times acceleration when we're in metric is always 9.8. Negative, sure. Depends on how you orient things. And then distance, how far is the rope going here? 45, right? Because it's 45 long. Okay, so we crunch that together. I'm assuming that's 13,230. Okay. There is something very wrong with that. As you pull the rope up, less of it is dangling over the side, right? As you pull this rope up, doesn't it get easier? Right? Like in the beginning, it's really heavy because all the rope is hanging over the edge of the cliff. But if you're halfway through, then you only have half of the weight of the rope that you are pulling. And so this is complicated because every millimeter you pull gives you a millimeter less stuff hanging over the edge, right? So like at every instant, the weight of the stuff left over is changing. So how about we just slice this rope? I'm just going to call that thing right there like a little change in distance. And I'm going to say that the rope particles that are in this little slice of rope basically travel the same distance, right? Like the ones at the bottom travel 45, the ones at the top don't travel at all. But if I just take a little thin strand of this rope, then pretty much all the things in that strand travel about the same distance. And so let's go ahead and start calculating now. So let's do the work for that one slab of rope. And we'll worry about the rest of the rope after we do this. So it's still mass times acceleration times distance. So m times a times d. Okay, let's fill in a couple of the easy things first. Acceleration is still 9.8. Okay, distance. How far does this thing have to travel? Well, it depends on where your slice is, right? So let's put a d someplace. There are two natural choices for d, either how far it is from the bottom or how far it is from the top. It makes no difference. From the top? Okay, so then we'll say that d can be this distance in here. You're just free to make your choice. So then when we come back to our m times a times d, how much is the distance? D. So I'm going to cleverly change it to a green D. It's not like blue D was just a theoretical distance. Right now it's specifically this green D that we defined. So I've left the m out of the picture because I think that's the Hard part. No? That's what's changing. Yeah. How much the mass of this guy is? Well, let's see. So it's 45 meters, the whole thing, and it's 30 kilograms altogether. So is there something I can do like naturally with these two numbers that would give me a sense of 45 over 30 would tell me how many meters per kilogram? You want to do that way or the other way? How about kilograms per meter seems, yeah. So we know that the whole rope is 30 kilograms per 45 meters, or 2/3 of a kilogram per meter. By that? Neither of those. Let's pause for just a second. Kilograms per meter, that's density, isn't it? Right, that's what we just found, is the density of this rope. It's just 2/3 of a kilogram per meter. How much mass you have in this little sliver depends on how long the sliver is, right? So we have delta D out of how much? 45. And I think we just have delta D times 2/3. No, we're not going to find delta D. That's just a variable. So I'll say it again. I think all we need to do is take this delta D and multiply it by the 2/3. Delta D is a number of meters, right? And we have 2/3 of a kilogram per meter. So if we had, for example, 3 meters right there, then you would just have 3 times 2/3 kilograms. Okay, so I think what we've decided is that the mass of this little sliver of rope is 2/3 times delta D. Delta D will become something familiar when we integrate. It will, DD. 2/3 delta D is this mass. Delta D is that small change in D. Change in D is just the name that we gave to how long this little sliver of rope is here. So the 2/3 kilograms per meter was a calculation we did to figure out how much mass we have in our little slab of rope. Okay, so that's the work involved in moving this one little purple slab from where it currently is up to the top. But then we take the whole rope and we slice it up into all those little slabs. And the work that we're going to do all together is the sum of the works of moving all these little slabs, right? You can just imagine them as being discrete things that aren't attached to each other. You got like 1,000 of these little slabs. You're just going to pull them up one at a time. And you're going to add up the work that you do all together. And then lo and behold, when you take a limit as the little slabs get smaller or more and more slabs, it becomes a familiar integral. So this will be our way to actually calculate the work. So we're just crunching in all the stuff that we've got there. 2/3 times delta D becomes dd. It's like a dx, and then times 9.8, and then times the d that we have there. This is like a dx, and this is like an x. Yeah. Okay, and then d, what's the range for d? We got to put limits here. 0 for the top guys and 45 for that last rope particle at the bottom. So 0 to 45 is it. Okay, so somebody just type that into the calculator for us. We're going to start the next problem, but we'll just get an answer. How much is it? 6615 joules. Okay. It is half, so again, there's a relationship happening here. So first of all, 13,230 was way too big, right? Because we weren't pulling the entire rope up the whole time. So why did it turn out to be exactly half? There's an average thing happening. Yeah, it's a, yeah, we've got like all these rope particles are the same as all the other ones, and for the let's see. So if we just looked at like the middle rope particles, then I think our calculation is reasonable. And then if you look at like the rope particles at the top, they have no distance to go, but the ones at the bottom have the entire distance to go. So on average, the top and the bottom rope particles are traveling the distance of the middle rope particles, right? Yeah, like everybody has like a counterpart that's on the other side of the middle, and everybody is it's basically just the entire rope is this one massive ball in the middle, and half is the answer. Yes, don't do that on my test. All right, moving on to 6. Who's our next reader? Let's go to Kevin for 6. 5 is just a formula that we can ignore. Okay.
Water tank keep great on a pipe as a column of water. I'm working on the tank water over the top. Water.
Okay, so we're taking this water from the cone and we're gonna pull it, like vacuum suction it up out to the above to the top and get it over the top of this tank. And so there's a certain amount of work involved, and the reason this is difficult is that the water particles have different distances they have to travel, right? The most work involved here are the particles at the very bottom. The least work is the stuff at the top because it just doesn't have as far to go, right? Okay, so let's start crunching through. So we know work is force times distance. And we're going to change here. I don't see any forces given to us, so I got to convert force to mass times acceleration, right? We've got that. But then we got to do even more converting here because the mass is not given in this problem, right? But didn't we see some mass formulas last class? Had to do with density. So do you guys remember that? Yeah, that's what we're going to do. So you guys remember this from last class? It's basically the definition of density is you take your volume, multiply by your density, and that's the mass that you have altogether. So I'm still converting here. This mass becomes volume times, and I forget if we're using rho or delta. I'll use that. So I think we've got all the pieces that we need. Rho for density. It looks like a P, but it's not the Greek P. What is the Greek P? What Greek letter is pi, right? It looks like our P, but it is not P. Okay, so I think we've got all the pieces that we need here. So let's go ahead and take a slab of this water, and I think Elia had the right idea. We're going to take this like cross section going straight into and out of the board, because every molecule in that cross section is basically traveling the same distance to get to the top, right? If you make the cross section thin enough, pretty much they're all traveling the same distance getting to the top. So that's why we're slicing it that way. We needed that distance to be constant, and so we're picking water particles that have a certain distance to travel. Okay, so let's do some stuff here. So how about we call R the radius of this guy? And how about we say delta H is the thickness of our water slab? What's the volume formula for a cylinder?
1/3 pi r squared.
Not quite.
1/8 pi r squared. Cylinder, you said?
Yeah, I want the volume of a cylinder.
Pi r squared times h?
Pi r squared times h is the volume, right?
Yeah.
Okay. Oh yeah, oh that's where the 1/3 came in, is the cone, right. But that little slab of water is approximately a cylinder. So we've got our pi r squared h formula for the volume. So I'm just going to copy all the other letters, and then I think we'll be ready to start plugging stuff in. Who knew when we just had force times distance at the start of this that it would expand to pi r squared rho AD. But I think we have all the letters we need now. Okay, so pi r squared. Okay, so pi, the r is what we call the r. We're just talking about the slab of water, so we'll just keep that as an r. The h, what did we call the height of that slab? Actually, delta h. Rho is the density of water, which is that given 1,000. Acceleration is still 9.8. And d is the distance we got to travel from where we are to wherever we're trying to get, and we don't have a symbol for that yet. So what letter do you want to use? So we could use d, but it seems like h, if like we got to have that delta h talking to whatever's gonna end up in the integral. So I feel like h is a natural like vertical distance. You have two choices. You can either let h be actually how far we have to get, or you can let h be the bottom part. I think they're both equivalent in terms of ease. For me, like if you said, what's the height of this slab? I would say, okay, height is always from the bottom to wherever. So my default is just to put the variable at the bottom, but it's okay to put it at the top. And so then I think that distance, so now we got to come up with a formula. So how far does that water have to go? Is 1, which is the whole thing, minus the h at the bottom. So we've got a magical pump that's going to take this thing, and our pump is has a circular cross section on it. It's like a big vacuum, but it's a circle, and we're just going to grab the top particles of water, and they're just going to go straight up, and then the circle gets a little bit smaller, and then we go down a little bit, and they're going to go straight up too. So everything is just going straight up. We're done. We're done. Yeah, you can't go from the bottom. If you go from the bottom, you'll do more work, right? Now, if you go from the bottom, then everything has to travel the whole. All right, so this is the work. This is the work done in moving one slab. That's what I'll put it down at the bottom here. So the work involved in one slab is this guy. So I feel like I'm ready to say, okay, we're just adding up the works of moving all of these individual slabs, and it becomes an integral. But what's the problem right now? You have r and you have h, and that's no good. Right. So we got to get rid of this r. Right. We like h because we've got delta h here. So we have not yet used the fact that the cone, the entire cone, is 1 meter high and 0.5 meter in radius at the top. So that's what we have to use. So we've done this before. We'll do it real quick now. Similar triangles up here tell me that the 0.5 of the radius of the big thing is to our radius, as the 1 meter height is to our height. Right? Whole cone to our cone, similar. And then maybe cross multiply. And we get the radius is half of the height. So then I'm copying everything else here, except the radius is about to change. What are we putting for the radius? 0.5h. There we go. Nope, no problem at all. As long as you, so I think you'd still need to change your delta H though, right? Yeah, as long as you had a delta H relationship. So if you want to do what Steve suggests, I think you got to take whatever equation you have here, take a derivative of both sides so that you have a delta R equals something with delta H. Yeah. Okay, so that's the work done with one slab. We add up the work for each of these slabs. It becomes an integral. We'll write the integral and we'll call it done. Integral pi 0.5 h squared. Delta h becomes dh. 1009.8. 1 minus h. Yeah, and just think about the water particles as a function of h. So how much is h at the bottom? 0, and at the top, 0.5. Right, that's just, yeah, so let's, everybody okay with that one? If we had made the other choice, which was to define h to be from the top to our slab, then how much is h for the top water molecules? It'd be 0.5, right? This between my hands right here is 0.5, and then for the bottom, 1. So it'd be going from 0.5 to 1. Yeah, if we had done this h, which seems to me more like thinking, which is why I always put my h just what's the height, and just from the bottom to whatever. Okay, it'll be the same answer at the end. This 1 minus h would change. This would become an h. Yeah. Anybody type this in for us? It's okay if we didn't. 200.44. Maybe somebody can verify that. So this is a work, so joules. And the last thing I'll say, for many problems that we do, there's this average kind of shortcut way, like the rope thing. We could have just done like an average type thing. I don't see a way to do an average here, at least not an easy way, right? I mean, you can find the average distance that the water molecules will travel. Let's see, it's ranging from 1/2 to 1. So 0.75 is the average height, or how far the average molecule is. But yeah, there's less water at the bottom, so you have to weight it appropriately. So I actually don't think that 0.75 is the average distance the water has to travel. Yeah, that's why we're using the calculus. How would you find the center of mass of the cone? Yeah. All right. Okay, activity is there. Raise the flag if I can help.